Ah, yes, Connect 4, the Game of Champions. Welcome to CS302 Assignment 1. As you can see here, we are going to be implementing Connect 4. We'll be using a linked list to implement the actual game board. We'll get into that details in a bit, but I'm going to first go over the rules for how Connect 4 is actually to be played. So the rules for a game is pretty simple. It's very much like tic-tac-toe, where you have two sets of chips. So you have either blue versus red or black versus red, or just two distinct colors basically. And you put them onto the board. And of course you want to have four in a row. So four vertical or four horizontal or four diagonal of the same color. And then of course that player wins. Now, just like in tic-tac-toe, the players alternate turns. So when one player, the red player, makes a move, then alternates to a blue player, then red, then blue, and so on and so forth. And of course, the game can end in a tie if, let's say, the board is filled up and there's no winner possible. Now we're gonna have an n by n board, but for our game, we're gonna have it as a 7 by 7 board, which I guess that's large enough, but not too large, not too small. So I think 7 by 7 is just a good size. So I do have a link right here in the description. So let me go ahead and sort of play this. So of course, there'll be a bright light flash will happen, unfortunately, but I won't really play this game too much. So, but here's the link. Let's click on it. Alrighty, turn the sound off. So anyway, here it is, Connect 4. So I'll play against, I guess I'll just I'll play against myself, I suppose. Let's try this out. So here's how it works. You have the 7 by 7, and of course, when let's say I'm red players going first, the chip sort of slides all the way to the very bottom. And of course, now it's going to be yellow's turn. So I guess in the game, I'm going to be having us implement, I have red and blue, but it doesn't really matter. So we'll have yellow. So of course, you can stack chips on top of each other just like this. And of course, you can play alternate like that. And of course, you can do this. And I'll just go ahead and just have red win. And there we can see 4 in a row. So the idea is how it's played out is that there can be 4 in a row horizontal or vertical or diagonal. Now, of course, the game can end if there's everything is filled up. But the way it works, you start from the top and it kind of the chip slides down like that. And of course, you stack chips up in each column, basically is how it works. So let's go ahead and now go back to the PDF and go over implementation details of how we're going to first create the linked list class, and then using a linked list class, how we're going to be able to emulate this board. So our linked list class is going to be a templated class, which makes sense because, as you remember from CS302, a linked list really can store any data type. So obviously for our main program, once we have our linked list created, we have to create our main program, which will be our Connect 4 game. Our template T is going to be a Boolean because I guess, true would mean red, false for blue, or vice versa. And right now we can see here in the linked list class, we basically just have our struct node. And of course, we have our T data, we have our previous and next pointers. So our standard doubly linked list. Now we're going to have this iterator class defined within the linked list class. So I'll go over how the iterator is going to work. I'm going to just, on the board here, just using pictures, draw out how the iterator has to be constructed. But this is going to be a way to traverse the linked list in main. Because remember, our pointer types will be private in our class. And we want to be able to sort of have the flexibility to traverse the linked list without exposing any pointer data. So this iterator is going to be really just our, I guess, pointer, if you will, but wrapped around in this class. And then we have our linked list class members right there. And we're going to have, of course, our classic head insert, tail insert, head remove is empty, our standard content here. Now, of course, this is going to be sort of a doubly linked list with a head and tail pointer. You might notice that in this implementation, as you see right here, or this class declaration, if you will, well, there isn't actually a head and tail pointer. We have this node star portal. I gave it the name portal because, well, we're going to have a circular linked list. We're going to have this pointer portal, which points some dummy node, and then that dummy node it points back to the tail and it points to the head. So it's going to be a way to implement a circular linked list. So of course, I'm going to draw how you want to visualize this structure. And of course, with the iterators as well. And of course, I have the write-up over here, which I'm not going to just read that to you because I guess you can read this on your own, but I will go over with a nice visual representation of this linked list iterator class. So let's go ahead and get to it. Okay, so for this linked list class, let's first start with the default constructor. So suppose in main, I were to go ahead and say ll_int like this. So I want to create a linked list of integers. Then I would do this declaration. So what happens is inside of our list object, we're going to have this portal pointer. This is our private member within our list object. Now, in this default constructor, I want to make sure I allocate a node to portal, which I guess that wouldn't be a big issue at this point. I think you'd be able to easily allocate a node to the actual pointer. So I'll leave that code for you to think about, but shouldn't be a problem. And we're going to go ahead and I'm going to separate this. So this node has 3 fields. That middle field is going to be the data field. The left field is going to be your previous, and the right is going to be your next. So of course, portal points to this node. We allocate this node dynamically to that pointer. I want to make sure I set portal's next equal to portal's previous equal to pointer, and then portal's next equal to pointer. So very simple assignment you have to do because portal, that pointer contains the address of that node. So I want to set portal arrow previous equal to portal, and same thing for next to make sure that they both point to the same node. So this denotes that we have an empty linked list. And of course, I'm going to put this line right there, which denotes that data field can be any garbage value, but we don't even care because we're never going to access portal's data field. You only care about that next and previous. So remember, it's a circular linked list. So it's going to point to the front and it will point back to the tail, essentially, is how it's going to work. So let's go ahead now go into doing some head inserts and sort of see how this linked list will be modified. Okay, so let's go ahead and just now call head insert and see how this image would update. So I'm going to just first, I'm going to copy this so I don't have to redraw this every single time. And let's say we have our list dot head insert. So I'm not going to cover tail insert in this video, but the head insert and tail insert are really about the same, just a little bit inverted, if you will, but same logic in both cases. So shouldn't be a real big issue with that. Okay, so let's go ahead and just paste this image right here. All right. So the way it's going to be done is this portal, this node is going to be your dummy node. So this portal's next will always point to the front, and this portal node's previous points to the tail. So for head insert, in this case, we can tell that our linked list is empty because if portal arrow next equals itself, that means you know it's empty. So we have a special case we have to construct for when we have a case like this. So we have empty linked list, we have to have a specific instance or have a special check and then do a special sort of unique code, if you will, for an empty linked list. So in this case, of course, we have this temp pointer and we're going to allocate a node to this pointer. Well, same idea. It's kind of a 202-ish type task. This part should not be anything complicated. Allocate a node to a pointer. So there we are. And of course, temp will point to this node. So this node will be your front and back at the same time. Now I'm going to first assign 11 to data field just because. So we have to make sure that this node is going to be the end node, so it has to point to that dummy node. And this dummy node's next is going to wrap around and point to that node like this. And then portal's previous will be also assign a point back to this. And then this node's previous has to point back to that portal node. So we can see that circularness going on over here because portal's next points back to the front and portal's previous points back to the tail. But of course, this node we have right here is both your front and back at the same time. Okay, and of course, then temp will be sort of gone after we escape the function. So here's going to be our current status of our linked list. Let's do another head insert to see what's going on. So we covered that one edge case where we had the case where we had an empty linked list. Now let's go ahead and sort of see how it's going to look after we do a head insert on a non-empty linked list. So I'm not giving you the code for it, but hopefully this helps you kind of visualize how you would write the actual code for this structure. So I'm going to now use my same list object. I'm going to call headInsert again. I'll insert 13 this time. So I'm going to just paste the original image over here, just like that. Okay, so right now 11 is your linked list front, and portal is your dummy node. It's going to be that node. That's going to be that one dummy node, which is going to be allow us to create this circular linked list structure. Okay, so now head insert 13 means I have to insert 13 in front of 11. So once again, in this case, we have a different case because we see here that since portal next or portal previous, they both don't point to themselves. They don't point to that same node. They point to a different node. So like, you know, the example up here, portal next and portal previous points to the same node that portal points to. But here, portal next and portal previous do not point to itself, which means you do have a node in the linked list. So we have a different case. We have our more generic case we have to write. So of course, again, we're going to create our temporary pointer, and we're going to allocate a node to this pointer. Well, that's again nothing too fancy. So we're going to have temp points to this node, and of course, I'm going to separate this node a bit, like so. I'll put 13 into the data field just to get rid of that part. Okay, so now this node 13 has to point to that front node. So 13 will be assigned to point to this node right here, like this. Now, of course, how do we get that node? So obviously 11 is going to be, of course, portal arrow next will be 11 because that's going to be your head node. Portal next will always be your head node. Okay, so we do that. And then, of course, what we have to do now is we're going to have to set this node 11 to have it point back to 13. So we're going to reassign this node to point like so. Has to point back to it because 11 is no longer the front node. 13 is that front node. So 11, which pointed back to that dummy node, now points to that new front node temp. And then temp's previous is going to point to portal. And then portal next is going to point to 13. And there's our new sort of setup of our linked list. So again, I did it sort of step by step, and in reality, you're going to have to write the code that does that step by step. So you have to sort of update each previous next pointer kind of one by one to get this scenario to happen. So that's the result of after inserting 13. Let's do one more insertion just to get a nice, good idea or a nice spectrum of how this head insert looks. So let me go ahead and just copy this. And I'm going to go ahead and just do one more insert. So I'm going to say list dot head insert. I'll say 5 this time. Okay. I'm going to then just paste this right here. Perfect. All right. Now, of course, temp doesn't exist anymore, obviously. Once the head insert function was called above, temp doesn't exist anymore. Temp was locally defined in the head insert function body. Okay. So again, we check. So the first thing we see is that our list is not empty because portal next or portal previous does not point back to itself, which denotes that this list is not empty. There's at least one node in this linked list. All right, so let's go ahead and now just have our general case we're going to have. So we're going to have temp. We're going to allocate a node to this pointer just like before. course, I'm going to add these lines in here to separate the node. And we have temp, and of course, I'll assign 5 into that node's data field. Okay, so at the moment, 13 is your front node. And how do we know that? Well, because portal arrow next is going to give you the address of that node. So notice right there, that portal node, its next field points at node 13. That's your head node. So of course, very simple to assign 5's next to point to this node, because we always know that portal next is going to be the address of that front node. So you first do that. Then you have to update. So 13's previous now has to point to temp from now on, because now 5's a new front node. So 13 has to point back to this front node over here. And then this temp node, its previous has to point back to that dummy node, or what portal points to. So of course, we just do a very simple assignment to assign this pointer to point over here. And then portal next is now going to be assigned to point to that node that temp points to, because that's going to be our new front node. And there we are. And now we know we inserted 5. So we have 5 in the front, then 13 and 11. Then 11 now, after 11, it points to that dummy node, which means that there's no more nodes that are relevant after 11. So I hope this head insert images right here helped you visualize how you would write the code for it. But you literally can sort of watch a video and sort of write the code step by step as how I drew it out. Because really, each pointer I redrew is just going to be one single line of code, a pointer reassignment. Now, for a tail insert, it's going to be very similar to head insert, but a little different. So I'll leave that part kind of open for right now, but that's going to be your head insert code. Okay, so let's go ahead and now go through the rest of our linked list class. Okay, so I went over to head insert, tail insert, same idea. Now head remove, you have to think about that. But again, remember that portal arrow next was always going to be your head node. So you have to basically have a few cases. So one, if it's already empty linked list, then don't do anything at all. And also you have the edge case where what if, let's say, portal arrow next. Well, I guess you have to also verify to sort of make sure that that node is the only node in the linked list. So of course, portal arrow next will give you that address of that head node. And if that head node's previous next point back to portal, that means you have only one node in your linked list. So you're going to have a special case for that as well. And of course, you have a generic case, which is a bit more simpler. So of course, you can write the same exact sort of code like you did for head inserts, like from CS302. The only difference is you don't have a head pointer, but portal arrow next is your head pointer. So that part, I'll kind of leave that open, leave that you work on that. But of course, you want to, draw the image out on paper or on your iPad or whatnot, and just do it step by step. And of course, as you do that step by step, each pointer redraw is one statement in C++. So that'll help you code this, but it's not so difficult, just a little different. An isEmpty function returns true if it's empty, the linked list, and false otherwise. Remember, if you only have just your dummy node in your linked list, that means it's empty. If that dummy node, that portal arrow next, is not pointing to itself, then it's not empty. So return false in that case. And a size function, it returns this standard size t variable. Now don't get alarmed. This is just really a very big, sort of a large unsigned integers. Unsigned really means that integers that can't store negatives. So for size variables, it makes sense because you can't have negative size, but it's just a very big integer is all this returns. That's it. So standard size t is just a very big integer that cannot be a negative, which makes sense because for sizes, you don't want to have negatives anyway. Now, for a destructor, you have to deallocate your entire linked list. So, one trick is you can actually just call head remove until your list is not empty. That's one trick. And of course, after you deallocate those nodes, at the very end, you want to deallocate that dummy node. So for a destructor, relatively not too complicated. Now, for your copy constructor and assignment operator, you actually can use tail insert in these two functions to one by one build up your linked list. Now, for your main, you might not necessarily use these functions. Now, if you do pass a linked list by value into a function in main, then it's going to actually call the assignment operator. But if you don't create functions in main, then I guess you don't have to worry about that. However, on code grade, I'm going to will test out to make sure you did correctly implement your copy constructor and your deep copy assignment operator. But again, similar concepts like in 202, but the only difference is that dummy node is going to be a little bit of a challenge to work around with that. Well, not really, because of course, you can use head remove to destroy the list, and tail insert can be used to sort of node by node deep copy your linked list. So now we have these two functions, begin and end, which are iterators are being involved. So I'm going to now go over how to actually utilize this iterator sort of class, and then go over how this begin and end work. But again, iterators, most of these will be very simple, a few lines of code for the most part. But again, they're just designed to help you iterate through a linked list in main. Let's go ahead and sort of do some examples of how iterators will be used in main, and hopefully I'll give you an idea of how the code would have to work, how you implement the code for iterator class. So consider our old list from before. I sort of redrew it a little bit. It's a bit more condensed, a bit nicer, because these ones were a bit more like this. It's a bit nicer. So anyway, so let's go over how the iterators are going to work. So to declare iterator in your program, there's a few ways. I'll go over the straightforward way, or more or less straightforward. So we have ll int, then we have our scope operator, and I believe our type is called iterator, and I'll call it IT for right now. So the actual sort of the logic here is that iterator is a type, but iterator is defined within the linked list class. So we have to have the linked list int first, then the scope operator, and then iterator is a class type defined within the linked list class. That's why we have to go through this extra layer right there. Okay, so in your linked list class, you have a function called begin. So the iterator type, I'll just sort of create this, I think I'll move this down a little bit. We have this, I'll call this IT, I'll sort of put here in green, I guess. So IT, and IT has a member called current within it. So I'm going to maybe put a box around this so it's somewhat. So here's our object, IT, and it contains a current field as a private member within IT. Okay, so in main, you can do something like this. You could say IT equals list dot begin. Now, what does begin do? Well, begin returns an iterator whose current contains that head node. So essentially for begin, what you want to do, so I can probably just sort of give some logic out over here. So within the begin function, you want to create an iterator type. So I'll just create iterator right here. Iterator I, I'll call it. They might wonder, well, how come I don't have to use linked list and then the scope operator to get iterator type? Well, if you're in the begin function, you're within the linked list class already, so you don't have to go through that. You don't have to do this. You don't have to go through that because you already are in the linked list class at this point. Okay, and now I'm going to say I dot current equals portal arrow next. So that's supposed to be I dot current equals portal arrow next. Remember, portal next is always going to contain the address of that head node. And then return I. So that's basically, that is your begin function. So then you return an iterator I back, and IT will be assigned I. So in a sense, it's going to assign it's current equal this i's current. So what's going to end up happening is, well, this is what's going to happen. it will point to that front node. That's basically it. Now, I want to be able to access that data field of that node that it points to. Well, how do we do that? Well, in our iterator type, we actually have this operator star function. So if I were to do something like, I'll just say standard cout star it, and I'll put a new line. That star it is going to be this dereference operator. Now, for pointers, remember, star operator will dereference it, but for iterators, you have to overload this operator in order for it to behave like pointers. So this function has to return the value 5. Well, the way we do that is within this, operator star for iterators, you would have to just simply, be one line of code, just simply return current arrow data. Because for iterators, so it in this case, it contains a private member called current, and we will dereference that current pointer and then access that data field, because current points to this node, and I want to access this node's data field by saying current arrow data to return 5. Then it will output 5 right there. So this right here, this is going to be the entire code for operator star. So again, relatively not too complicated. So now, what if I want to move to the next position in the linked list? What we have is ++ operator. So remember, we actually have a prefix or postfix operator. So we have it ++, or we can do ++ it. Now, this ++ it is a following function prototype, or I'm going to have a subset prototype. So if we do operator ++ int like that, this implies that int right there just tells the compiler that I want to have this unary ++ operator be a postfix operator. So ++ appears after the variable. But if I have this one, operator ++ like that, that implies it's going to be a unary operator, but it's going to be a prefix operator. So that's how ++ being in front of iterator means it's a prefix operator. So both of them will do the exact same idea, but a little bit different though. Now, at the end of the day, it will point to the next node. So it++ or ++ it, either way, the result of it is going to be to move it's current to point to the next node over, which is pretty simple. We would just simply do current equals current arrow next to reassign it to point to the next node. But the only difference is that operator ++, both of these, return an iterator object. So this ++ like this, it++, is going to return essentially, so let me just go ahead and let me just try to redo this for a second. So for the operator ++, the postfix operator, what's going to happen is it's going to move this current over to this node, and then it's going to return an iterator that points to this node, the node that you had before you moved the current over to the right node. So of course you have to create an iterator object within this operator function, move the current over, but then return the previous node that current pointed to before you moved current. For the prefix operator, so for this operator, for prefix operator, what you will do is you're going to, again, move it current over to this node, And then you're going to return an iterator that in fact points to that node. Now, again, if you don't get this correct 100%, it's not an issue, because really, I wouldn't imagine any of you would do anything so bizarre. But in reality, the only truly important sort of function of ++, the prefix or postfix, is that it's current has to be moved to the node after, and then the next node over is the idea. So now, oops, I shouldn't have moved. Let's keep it like this. So now after I do ++, either one of these two the same result will happen. It's going to move it's current to point to that node. So if I were to now, again, just say star it, this is actually going to output 13, because it's going to essentially call this function. It's going to return current arrow data, because star operator just simply is a one-liner, just return current arrow data. And this iterator, its current points to that node. So current arrow data means retrieve 13, return 13, and it will display it right there in main. So that's basically how you want to actually work with iterators. Now, of course, you have the comparison operators. You have equals, equals, not equals. Well, for those operators, you want to compare the currents. So essentially, if you want to go ahead and do something like if it equals equals list dot end. So remember, list dot end returns the iterator of the dummy node. So begin returns this front node. The end function, returns that dummy node. So begin returns this node, the front, and end returns that dummy node. So when I say if it equals equals list dot end, I'm going to be comparing these two iterators' current fields. So it.current, and then this temporary, or whatever this iterator is, list.end, is going to compare their current fields. So really, for the operator equals equals, all you're going to be doing is just comparing. So you're going to return this current equals equal, I believe I have as RHS for right hand side dot current, a single liner. So essentially, I'll use red over here. So this arrow current is going to be it's current, and then RHS dot current is going to be this iterator's current. So we're comparing their current fields. If they're the same, then they do in fact point to the same node. So that's really all there is to the iterator type. So I have written some code as well for you. I'll go over this right now really quickly also. So you can do the following loop to iterate through a linked list. So you could say something like for llint it equals list dot begin, and then it not equal to list dot end. Then I'll sort of two-line this it plus plus. And of course, you can just just output, I suppose, star it. And of course, that's it. That will traverse your linked list. We first set this iterator to point to the front. And once it hits that dummy node, then it traverses the entire linked list. And then of course, we update this to the right by 1 every time, after every iteration of this loop. So that's how you can traverse the entire linked list. So there's that. I have that in the PDF. I want to sort of talk about this. And also you have an alternative way as well. So since we are using C++ 11, you actually can do this. And of course, I will just see out the iterator. So what auto does is that essentially here we have this it variable, and we're going to assign it list.begin. So list.begin is an iterator. It returns it, and it's going to assign that to this variable it. So then the auto is going to essentially just automatically assign a type to it based on what sort of variable we're trying to assign to that variable. So also, just to extend this further, if I were to do something like this, if I would say auto x equals 7, then x is going to be an integer data. But if I were to also, let's say if I said auto s equals hello world, a very infamous string, then this variable s is going to be a string variable, because this right here on the right hand side is being assigned to s, and since this is a string literal, then auto will be automatically sort of replaced with the word string essentially. So anyway, that's your linked list class and iterator. So hopefully this gives you an idea, and I did give some code for iterators as well. So anyway, now for the last part, we're gonna have to go over how we can implement this game Connect 4 in main. Let's get to it. Okay, so in main, you want to implement this game board. So what I have declared right here is you're going to have an array of 7 elements. Each element will be a linked list of type bool. And the reason why I'm choosing a bool is because, well, each node in a linked list represents a chip color, red or blue. So true or false binary is a perfect way to store this. And of course, each of these will be its own individual linked list. And we can think of it as this is going to be essentially your column index. And then we're going to stack nodes up in each column. That's how we can visualize this structure. So in the program in main, you're going to read user input. So as you can see here, I have these numbers here in green. It's going to be our column indices. And below I have the letters. So in main, you have to display to the user A through G. But behind the scenes, it's going to be 0 through 6. So when the user actually enters a column, you're going to read in the input by character. So for example, if the user reads in character D, then this formula will be able to convert it to the proper index. So I take the to lower of the user input, minus it by character lowercase a, that's going to map me to a position. Now, if this number is a negative or above 6, then the letter was not between A through G, which means that's invalid input. But here, since it becomes 3, which is between 0 and less than 7, then we can, of course, do the following. So board 3.tailInsert true will put a chip into this column. So I guess I'm going to say true is going to represent the color red. So what happens is it will stack a node. I'm just going to use just R for red right there. But it will stack a node that contains true for its data field into this column. And likewise, if let's say the next user tries to also insert a column D, then of course it would map it to index 3 once again. Let's suppose I do a tail insert again on this column. And I'll use false. I'm going to put a blue chip. It's going to stack this on top, because tail insert means it puts it to the end. But I'm sort of inverting this array in this sort of format, so it's easier to visualize how this Connect 4 board will be set up. And of course, we just stack them on top. So tail insert always inserts to the back of that list, so it's going to emulate that stacking of chips onto a particular board. So of course, in main, you have a Boolean variable, I would imagine, that will sort of, you would flip that Boolean variable after every single turn. So that way it alternates from red to blue and so forth. And of course, if it's out of range, you of course can't insert a chip there. And also, if let's say if one of the columns already has 7 nodes, you can't insert a chip there either. But of course, you do have a size function, so you can do board index3.size, and if it equals 7, then you cannot insert a chip there because we don't want to overflow this. So, there's a very simple checks we can do. So that's going to be our first part. Now, outputting this board to the screen is going to be a little bit of a challenge because, as you can tell, you have to sort of output from top to bottom. So you're going to first output, all of this content. You have to output all of this first, and then output the letters afterwards. You have to start from the top, work your way down. So of course, in these elements over here, we can see there's no nodes over here. You have to find a way to actually determine that you have to output a dash symbol instead of B or R. Now, of course, you're going to have a nested for loop of some sort that will tell you, so maybe you start that loop, maybe for this is going to be like your row indices, if you will, and you can start it from 6, or I guess 6 or 7, whatever you want to use. And then of course you verify if that column doesn't have that many nodes, output a dash. But once that inner loop counter works its way, actually I think it's outer loop. I guess I have to double check my code, but I guess I'll let you figure this out. But once you have a case where this counter works its way down over here, you notice that this sort of column does have enough nodes. So you set the iterator to the end, output that node and work your way down, doing that minus operator for the iterator to move the iterator down one level, and output each with output B, then R, and then of course you hit the dummy node, obviously, so you're done. But in this column right here, well, there's no nodes at all, so you have to make sure that you output dashes. But here you output dashes also until you finally have a case where now, when you hit this index, so you can have some type of a counter, and once it equals the amount of elements or less for this column, you then start outputting the actual node, the B or R letters like that. So not complicated, but not straightforward either. So just think about that. So you can have really a nested counter control loop. And you have to make sure that you have at least the correct number of nodes in that column so you can begin outputting everything. So it's a little bit of I guess you have to think about that for a bit. Okay, so now let's go ahead and go over some of the logic for how to verify if the blue or red wins, how to sort of determine if 4 in a row has been achieved in the game, and so forth. Let's get to that part next. Okay, so the most simplest way to verify connect 4 is going to be in that vertical direction. So suppose that we have the following, let's say maybe in row 2, we have red, blue, red. Actually, I'm going to have 4 in a row like this. Let's say we have this scenario happens. It's probably not likely to have this situation, but let's just suppose we have this situation. So we can see here we do have 4 reds in a row vertically. The logic will be the most simplest for this one. Let me go ahead and sort of put a few other, maybe just sort of put some other chips here and there just so we can kind of get an idea of what we could possibly see. So it's, I don't know, so this is going to be, I guess, a good enough example, we'll say, for right now. So you want to, first go through this board and verify if you can see any vertical 4 in a row. So the first thing you do is I'm going to have really 2 iterators. So you're going to have a counter control loop. You first start from column 0. And you want to set an iterator to the beginning position of column 0. So you have one iterator that's going to be pointing right here. And then you're going to have another iterator that's going to be just one above. So maybe I'll use this color to distinguish these two. I'm going to then compare these two, so by using that star operator to retrieve that data field of those nodes and compare them, you can see here they're not going to be the same Boolean value, so we can't get 4 in a row. So we're going to then adjust this green iterator to where the pink iterator was, and then we're going to increment this pink iterator to go above the green, which now this pink would be at the end. So that means, okay, well, at this column, we didn't obviously find 4 in a row. Okay, so we now go to the next column of this board. So what happens here is we're going to set this blue iterator to point to this first node. So of course, the board at column or index 1 dot begin will set that blue iterator to that first node. And then we're going to set our next iterator to a node after the blue one, which I guess this case would be the end node because it's going to be after that R node. There's no more nodes in that linked list. So then we're done because we obviously can't get 4 in a row, because once we have a case where we hit an end iterator at some point before getting 4 in a row, that means we know for sure there's no way 4 in a row was possible in that column. Okay, so on to the next column. Let's set an iterator right here. So we're going to say board index 2 dot begin, which will set the iterator to point to that first node in that linked list. And then we're going to have another iterator that will go to a node after the blue one, which will we just simply set that pink iterator. Actually, I guess the real code would set it equal to the same iterator like this. And then we just do a plus plus operator on that pink iterator to move it up 1 node. Then we compare. They are in fact different from each other because the pink and the blue ones are going to be blue and red accordingly, so which means that there's no match. So we're going to adjust this blue iterator to now point to this position and then set the pink iterator to the one above. And again, we see there's no match, so we have to move the blue iterator up 1, and a pink iterator is going to move to the one after, like this. Now, in this case, we do see a match, so we're going to keep the blue iterator at that same position, but move the pink one up. And right there, another match happens. We have so far 3 in a row. Move it up again. Another match, we have 4 in a row. So at that point, we're done. So you may want to have a function possibly that you pass in this board array into that function, and it's going to basically just return, some type of data, either a Boolean or could even return maybe an enum type or return an integer of some sort that tells you that you got 4 in a row, and it's going to be red 4 in a row, and that way the game is over. So this one is going to be by far the simplest sort of check. The 4 in a row vertically is very simple because you have to sort of just iterate through that linked list using 2 iterators. You have one that points to that starting position, other one will move through other nodes. Now, if at some point we have a mismatch, you move that blue iterator to that position where mismatch occurred, and then from there you're going to restart and have your pink iterator move again. So trying to find that range basically that has 4 in a row if it's possible. So hopefully this gave you an idea of how to do 4 in a row vertically. Now let's go ahead and go over our other checks, because you have to also check for a diagonal, which is going to be moderate difficulty. And then of course the horizontal check is going to be, at least from my experience, definitely the most difficult one to check. Let's go ahead and now work on the diagonal check next. Okay, so let's go ahead and now talk about the diagonal approach. So also, after every user makes a move, you want to right away check every possibility to see if a win is possible. So you want to first check for the horizontal, diagonal, or vertical, any order you want actually. But you want to check every time a user makes a move to see if after a move has been done, is there a winning combination. So let's go ahead and go over a case where maybe we have a diagonal. So let me just try to create an example that's kind of pretty good at least. So I guess we'll have I guess 4 in a row red. So let's see, I think this situation is possible. Let's see, yeah, this looks so far so good. Then we'll put blue over here. Then we'll put red here. Say the users make this type of scenario. So we have blue, and then we have red like this. So we can see here we do have 4 in a row diagonally. So again, we have to, there's really no shortcut. We have to kind of brute force it. You have to go through every single column, and for every node we see, we have to check if it's possible to have 4 in a row. So we first go through our first column, column 0. It's empty, so there's no point to check over there. Then column 1, we check. We'll have an iterator pointing here, so we do have a node right there. So we have to go to the next column and then go one iterate. We have to move up 1 spot because we have to make sure we have to be checking essentially this node right here, right? But we see here in next column, there isn't, there's only 1 node. So that means there cannot be a diagonal 4 in a row. So that means we have to go to the next position. So our loop counter increments the next element over to this position. Okay, so we see it's going to be a red node. So we go to the next column and we check. Are there at least 2 nodes? Yes, there is. So we start from this next column 3 at the begin and we increment it by 1. And we check, it is red. Okay, so far so good. So now we have to go to the next column. The next column over is index 4. And it has to be 3 elements. At least 3 elements has to exist over there. So you have to be mindful of your counters essentially. So we have 3 elements over here. So we have to start from the beginning and then move 2 spots up. So we start from here, increment this iterator twice to go right there. It's a match with that blue iterator. So far so good. We go to the next column, column 5, and we have to check. There has to be at least be 4 elements over there. And there are 4 elements. So you move the iterator, we start from the beginning, as always, and we have to move 3 times up. We check, this is also a red, so we have 4 in a row, so we're done. So that's kind of the general case. We have to also check for edge cases. So for example, what if, let's say we had this situation like this. So here was a case where it does come out, correct. But what if we had this, for example? Let's say we have a case or scenario where, what if we didn't have that right there? Then what happens is, well, okay, so let's say we do the same thing. We start off here. There's no way to get a match. We go over here. The next column over has 2 elements. So we have our pink iterator starting off at the beginning. We move it up 1. We find a match, so perfect. And then we go to our next column, column 4. And this column, we don't have 3 elements over, which means it's a failure. So that means we can essentially move this blue iterator over to the next position and then start again. Okay, so we start from this next position. We go to our next column, column 4. We have at least 4 elements. So we have our next iterator, our pink iterator, start off at the front and move it up 1. We have a match, so far so good. Then we go to our next column, column 5. Do we have at least 3 elements? We do. So we start off at the beginning, move up 2 times. We have a match, perfect. Now our next column is empty. So again, there's no possibility for a match. So then what's going to happen is I move this iterator, this blue iterator, up to this position. And see from this spot, is there a possibility of having 4 in a row? Okay, so we check over here. The next column over has only 2 nodes. So there's no possibility of having 4 in a row from that position. So we increment our blue up to the next position. It's now going to be the end. So we're done with this column. On to the next column. We start off over here. We check for 4 in a row. So next column, we set this iterator to the begin and increment it by 1. Not a match. So then we try to move this blue iterator up over here now. And then we go ahead and from this position, we have to check the next column and it has to be at least 3 elements over there. And there is. So we start off our pink iterator here, move it up twice. We do have so far 2 in a row, so perfect. But then next column, it's empty. So then we move our blue iterator up to the end. So we hit the end of this condition. So we try to start all over again at the very next column at the beginning. Now, you could make it a bit more efficient, but I try to make my code very generic. So I don't want to have to do too many edge cases. This kind of handles every possible scenario. So you have to have some nested loops, you have to have nested counters. And let's say, for example, like you were right here, let's say we were here earlier, let's say we were right over here, then we have a counter that tells you, I guess, 1, that tells you that this next iterator has to move 1 spot up. And then if you go to the next position over here, we have to now increment our counter by 1, which tells we have to move 2 spots up. So let's say we had a red index over here. Then this next iteration, we have to know, okay, we were this is the first position, second position, now we're in the third position, or third iteration of this inner loop. And we have to move this counter up, first was, only in this situation, we moved up only 1 time. Here we have to move it up 2 times. Here we have to move it up 3 times. So you have to have some counters that tells you how far from the beginning do we have to move that pink iterator up, so then we have it aligned diagonally. So again, I think it's simple to understand how it works, but then coding it is a different story altogether. But hopefully this gives you an idea. But you would have to have a nested sort of for loop, a counter control, and that counter tells you how many elements you have to move that pink iterator from the beginning, how many times you have to move it up to get it aligned nicely. And of course, you have to also do it in the other direction as well, because you could have 4 in a row, in this direction, you could have it, possibly. So you have to do it, sort of in that upright, or I guess you can say that northeast direction, and that northwest direction you have to be checking for. Now, that's how I did it. Of course, you can do it differently, but I'm giving you a hint as to how I did it. This method is a little bit not as efficient, but it was easier to code it. So anyway, that's your diagonal check. Let's now go a little bit into the horizontal check last. Okay, so let's go over the most, at least for me, the most difficult check, which was the horizontal check. So again, it's going to be a nested for loop, very similar to the vertical check, but you're going to have to invert your counters a bit. But the hard part is going to be that because each row, so I'll just draw this out here, each row, there is no index for this. They're all going to be nodes. So you can't just, it's not going to be a matrix. If it was a matrix, this would be a lot easier to verify this, but it's going to be a little bit of a challenge with iterators. So what you would do, of course, is you start an iterator, you put iterator right here at the very beginning. So you start from column 0. And then what you do is you have your second iterator, go to the next column, you compare these, and they are in fact the same. So far, so good. You go to the next column, and it's empty, which means that at this point, you're kind of done. So what you want to do is you want to set the iterator, you want to essentially start it off on column 3 now, because you can kind of take that blue iterator and just slide it over to the right, because you know that from 0, 1, and 2, there is no possibility of having a 4 in a row. Now, from here, you're going to set iterator, a pink iterator, right there. You check, they are the same. So move it over to the right, and then set it to the begin. So you have to go to index 5, set it to the begin for this pink iterator. You check, and they're the same. So then you go to the next column. So you go to column 6, dot begin, which will set iterator point to that first node, and we see there's actual a mismatch right there. So you have to set this blue iterator to go beyond the bounds of the array, which means now you know that first row has been taken care of. So you're done there. So now what you do is you have a nested loop. You're going to start off at index 0 again. But then this time you're going to move this blue iterator. You start at the beginning, and you move it up 1 spot up. So you have this other counter that tells you what row you want to begin for this column. And then that counter tells you how many elements up you want to move that blue iterator. So then what you do now is you go to the next column, column 1, begin, and you also move it up 1 spot, because you want to make sure you're aligning these nodes together. And you check them, they're the same. So far, so good. Go to the next column, Column 2, you have to at least have 2 nodes, and you don't have 2 nodes. The size will tell you how many nodes you have. It would be obviously 0 for column 2. So that means, obviously, you can't get 4 in a row, so you're done. So you want to essentially move this iterator over to now index 3, and then move it up 1 to be at the the next row of this board. Okay, so now what you have to do is, starting from index 3, you go to the next column 4, start at the beginning, and you move it up 1 spot, because you know you're at the next row, so you have this counter that tells you how far up you want to move that iterator, so it's going to be in that same row. You check, they're the same, so far so good. Go to the next column, column 5, at the beginning obviously, and you have to move it up 1 element, and we check they're the same, so perfect. Go to the next column, column 6, start from the beginning, and then move it up 1. And oh, we got 4 in a row. So now you're done. So you want to almost think of the logic as if you really did have a 2-dimensional array. So you're going to have these counters that tells you what column and what row you want to be on. But because you have a linked list, you can't just magically jump to to row 1, row 2, row 3. You have to have the iterator that moves, that many spots up, so that way you're going to be in the correct row. So just try to visualize it like you're using, as if you really were doing a matrix. In fact, maybe for all of these checks, for the diagonal, horizontal, vertical, just assume that you have a matrix, but then you have to sort of update or modify it a little bit, because you can't just jump to a particular row. You have to increment your iterator to that row, but that's the only challenging part. Now, there are some edge cases to consider, because you could have a case like this. So what if you had this scenario where, let's say, you didn't have an element right there. So of course, you start here, or you would start here and then move the iterator up. And then you have your pink iterator right there, move it up 1, it's a match. And then this next column, 5, you would notice that, oh, the size is not big enough. You don't have enough nodes right there. So if you try to start the iterator here and move it up 1, you would go to the end iterator, so that means you're done. So of course, the size could be used, or also if you hit the end node, as you try and move that pink node up, that means you don't have enough nodes in that linked list. So of course, the size can be used, but also once you hit the end, for some reason, as you're trying to increment that pink iterator, that means you already went beyond the bounds of that linked list, which means there weren't enough nodes right there. So this had a few edge cases for me. Maybe I didn't think about the logic correctly. I'm actually thinking about this right now as I'm doing this video. I see how I could have done this actually better, but too late now. I already wrote the program, so I'm not going to modify my code now. But anyway, that's going to be the logic for how to verify sort of a horizontal 4 in a row. Let's now go over the tie sort of logic, and then of course some final remarks for the assignment. Okay, so for checking for a tie, that's relatively going to be the simplest one. So what I would first do is just first check for 4 vertical. So check for if it's 4 vertical, 4 horizontal, and 4 in any diagonal direction. Now, after all those checks, if no winner was possible, then you check to see if every column is maxed out. So if every column is maxed out and there's no winning combination, that means you can assume that that has to imply a tie had to have happened. So that's kind of a simple check right there. Okay, so now for our final remarks, here are just a few specifications to consider. So of course you want to use a linked list and iterators to traverse the list and verify it. Now, you don't want to create extra nodes into your linked list. So for example, outputting your board, let's say over here. So you put these dashes there because there's no, let's say, you don't have that many chips stacked up. So for example, let's say I enter row B and it puts the red chip right there. So I mean, one trick would be to have like, a linked list of integers, let's say 0, 0, 1, -1 you could do, right? You can put stack a bunch of null or dummy nodes right there to make it easier to traverse it. So You can't do that. So you have to basically know the size of each column so you know whether to put a dash over here or to actually output the correct chip color. So like for example over here, as you're traversing, you have to have maybe a nested for loop with a counter, and you know that you don't have 7 chips or 6, 5, 4, 3, but you do have 2 chips. Then you can of course then begin outputting using an iterator. You can start from the top and then move your way down until you hit the front. So output red and then red like that and so forth. So you don't want to have dummy nodes like that. Also, you don't want to create a 2-dimensional array at any point. That would be cheating if you did that. So if you do that, that would be a pretty major loss of points. I don't know how many, but it would be a pretty big amount of points being lost if you did that, because you're kind of, it defeats the purpose of the assignment, of course. So you don't want to create additional arrays either. You only want to just use, you just want to simply use this array of linked list. You can create additional linked list objects if you want. That's okay, but you can't really, you're not able to create additional arrays. That would make the program too simple. It's no 2-dimensional arrays of any kind like that. Yeah, I guess I also put this here as well. Same idea, so I wrote that there as well. So of course, make sure you have your code well documented and make sure your program is memory leak free. So we will, on CodeGrade, we're going to verify if your program doesn't in fact generate memory leaks. Also, we're going to have additional checks on CodeGrade that's going to make sure your program does implement the deep copy constructor and assignment operator correctly as well. And also for this program, on CodeGrade, you have to submit 2 files. ll.h, your header file. So since you're using templates, you're going to simply have your header file. You're going to put all of your code in that file. So you're going to have in your header file, you're going to first have your class declaration, and then below you're going to implement your functions as you would as if you were to separate the files. But you can't separate them because with templates it does cause some issues. So your ll.h will have all of your linked list, class, iterators, all that will be implemented and declared in that one file. Then you have a separate main file. So of course you want to call it main.cpp. I have the CodeGrade set up where you won't be able to submit unless you give me a file called ll.h and main.cpp. So then in your main file, you don't have to actually do separate compilation. You have to just simply include your ll.h in your main file and then just simply g++ your main.cpp. That's all you have to do, and it will compile and link those 2 files together. Now I'm being strict on the actual file names because I'm going to create additional main files I'm going to have and link those to your header file so I can test out the deep copy constructors and so forth. So of course, here's a sample execution of your program, but I do have several tests on CodeGrade that tests out, 4 in a row horizontally, vertically, and diagonally, and a tie as well. Here's one case, so you also can look at this as well. But on CodeGrade, I actually do have all the possible checks on there as well. Additionally, CodeGrade will check for deep copying as well, so make sure you did correctly implement that. And that's about it. So I hope this video did give you a good idea of how to implement this program. So I guess happy coding, and till next time.